Welcome everyone. Today we will be talking with Dr. Richard Ernst and Hafida El Bilali from Carleton University in Canada. And they recently published a paper in Nature Communications where they are tracing a magmatic dike on our neighboring planet, Venus. So a magmatic dike is a lateral movement of magma beneath the surface of a planet. And the dike they're tracing on Venus is about 3,700 kilometers long, which is really long compared to what we have on Earth, where the longest dikes are around 2,000 kilometers, the one in Canada, for example, which I think you also mentioned in your paper. So today we will be learning more about this dike, but also what this dike and its features tell us about the geology and the volcanism on Venus. So to start off, Richard, do you want to explain in a little more detail what a dike is and why you are studying them on Venus?
So I'm Richard Ernst, and let me take that first question. Basaltic magma, which is what we see a lot of places on Earth and also on Venus, has to come from a mantle source, and it comes up via these vertical cracks that we call dikes, magma-filled cracks. And so the magma comes up and also moves sideways in the crust as a vertical crack, maybe only 20, 30, 100, maybe 200 meters wide. And that's carrying basaltic type magma that then can spill out onto the surface as lava flows.
And why are you studying them on Venus? What's so exciting about Venus?
Venus is covered by about 80% of basaltic volcanism, and we think that much of that basaltic magma, has to have come and been in place via these vertical magma-filled cracks. And we're understanding that many of these cracks on Earth, and we now are recognizing on Venus, have giant radiating patterns and giant circular patterns, reflecting their links with big magmatic centers. And so, as Dr. El Bilali will talk a little more about the one that's the focus of this manuscript, but the idea is that you can have radiating swarms that go out 3,000 kilometers or more, and the magma is thought to have been coming up in the central region and then being spread laterally sideways via these vertical cracks and then spilling out at the surface at different places. Okay,
so it's really a tool to better understand the volcanism on Venus and its geology.
Yes.
All right, thank you. As a follow-up question to this, what kind of data are you using to study this, and also where does this data come from?
So we use the main data we use in this research was collected during the NASA Magellan mission between 1989 and 1994, and it includes synthetic aperture radar, which we call SAR images, including also altimetry, emissivity, and gravity data. So using these images, we get these images from US Geological Survey, and we bring these images and we use them for mapping. And geological mapping was in this research, or any research on Venus, is carried out using ArcGIS Pro to enable more accurate and the detailed interpretation of these images. We also actually use what we call Java Mission Planning and Analysis for Remote Sensing, and we call it a JMARS. It's really helpful because we can make profiles in these images, and we could navigate all Venus if we want to go outside of our mapping area to get more information. That will help us in the interpretation.
Given the data is already, I think, more than 30 years old, are there any drawbacks or caveats in using this data in terms of quality?
The problem is not the data are good to work with. There is a resolution is not especially for topography. We have, I think, the resolution is not as good as we need, but those future mission, we count on this future mission to get some more high resolution, especially topographic data to study and map in our areas.
Oh yeah, so let's move back to the actual dike you are tracing and describing in your work. In the opening statement, you said that the dike has a volcanic origin. Could there, also based on the scarcity of the data, could there be another possible explanation for this? Like, could it be a tectonic origin?
We considered other possible origins for such a long, 3,700 kilometer long, linear, narrow, just 2 kilometer wide feature. Other kinds of things plausibly that could be such long and linear could be, a thrust fault, but there's no difference in topography on either side of it, north or south of it. Could be a major strike slip fault, but we need to see no offsetting of features north and south of it consistent with that. The other kind of thing that can be long and relatively narrow is a rift zone, a place where the crust is starting to pull apart, but such rift zones are never so long and narrow. They're much wider. They're wide on Venus, tens to hundreds of kilometers often, and then potentially thousands of kilometers long. So it does not match in appearance any of these other kind of plausible things for long, very narrow feature on Venus.
So that was a major question. So to know if it's tectonic or if it's dikes, we have established criteria so to recognize dikes on Venus. So when we have dikes that converge to a center, those are radiating dike. These are actually dike. They are not tectonic, but these are dikes radiating from a volcanic center or magmatic center, like the case we have on Alzamon and other centers on Venus. We use as a criteria a pit chains. When we see a chain of pits, these are collapse feature above a dike or surface expression of a dike, then we know that we have a dike underlying these pits. Because on Venus, we see actually graben, we don't see dikes because there is no surface erosion. But when we see a chain of dikes, of pit chains, then we have an evidence that we are seeing dikes. So convergence, pit chains. We can see also sometimes a chain of shield volcanoes. There's a lot of shield volcanoes on Venus, but sometimes we see shield volcanoes aligned along a graben. So this is also a criteria that we use to establish that we are actually, this is a dike and not a tectonic feature. And the other criteria we use is sometimes we see a dike and we see a lava spilling out of this graben. So it means that also that we are actually, this lava is emanating from a dike and it's not a tectonic features. And this is applying also to the Great Dike of Atla Regio, because it seems to be converging towards Alzamon. So it is considered to be a dike emanating from this volcanic center.
And what does the dike, or your results that you're presenting on the dike, what implications can we draw from this on the current volcanism or tectonic situation that's going on Venus?
So Atla Regio is a major metal plume center, like other region on Venus. We have a BAT region. There's a BAT region, which include Atla Regio, Beta Regio, and Themis Regio. And all these major plume center are they are reported to have young volcanic. They are youngest plume centers on Venus. For the implication of the Great Dike, one of the implications is that this dike is able to transport a large amount of magma for a long distance. So the implication is that we have a magma chamber that is buffered. So it's empty and filled, and the dike is moving the magma far away from. So it's always it's fed by this magma chamber. And this magma chamber is never empty, so it's continued to provide magma for the dike to transport as long as possible away from the centers.
About it, in a geological sense, such emplacement of a great dike is a geologically instantaneous event. So it becomes a very precise time marker over vast distances, in this case 3,700 kilometers. So we see things along the way that it cuts, and we see things along the way that are locally cutting it. So we get a very precise time marker. And the other thing about it is its trend. It's radial out to about 1,200 kilometers from the plume center, and then it swings in trend and becomes parallel with the huge Parga Chasma rift system. And so it is coeval with, it's coming at the same time as there's active extension in this Parga Chasma rift system. That system's 10,000 kilometers long, and the Great Dyke tracks along it for at least 2,500 kilometers. And that is telling us then that Parga Chasma, which is one of 4 rift systems that are converging on Atla Regio, are all coeval with the Atla Regio plume center, and also specifically coeval with the timing of the Great Dyke. Also, the distance at which, maybe to mention, the distance at which it swings in trend is really significant.
So we noticed that those dikes emanate converging to Azaman, including the Great Dyke. They swing at a certain distance of which is 1,200 kilometers. And in our research, the dike swing at certain distance is give us information on the size of the mantle plume. And the 1,200 kilometers is also a radius of the mantle plume of Azaman, which was a huge mantle plume centered on Azaman. And the diameter of this plume is 2,400 kilometers. It means it's not only a simple plume, it's a super plume. So that's we call it now Atla Regio super plume. And at that distance, when it swings, and the Great Dyke swings exactly at that distance of 1,200 kilometers. So it's consistent with what we found, that the size of the mantle plume is 2,400 kilometers, and all this region is still at the plume head stage, so it's still active.
As a final question, do we know the age of the emplacement of this dike?
We know the age of the emplacement of not exact age, because we don't have age, absolute age dating on Venus. We just try to have a relative age dating. But the age, because we are still at the mantle plume stage, so the age will be 50 million years or younger. So that's what we, Richard, you can comment more on that if you want. But this is the age that we have, and we think that it's an active, still active mantle plume center.
I don't. That's great. No, I mean that the point is, yeah, it may actually, it's still active. It's still an active plume center. We know from Earth that major plumes and their magnetism, which we call, and the magnetism on Earth we call large igneous provinces, we know that they, are typically very short duration events, but can last up to tens of millions of years. And so that gives us a constraint where we think Atla Regio and Azamans are still at the plume head stage. They haven't gone to a Hawaiian style hotspot sort of story yet. So they're still at this active plume head stage, and that means they're probably less than 50 million years old and still active.
Here we are here. This is Azaman, the center, the main center in Atla Regio. This is Atla Regio mantle plume center. You see those 4 arms rift zone. This one and this one. This is called Parga Chasma, which extends for 10,000 kilometers. This is called Diana Chasma, which extends for about 7,000 kilometers. This is Hekati Chasma, extend about 8,000. And this is the youngest chasma or chasmata is equivalent to a rift zones. And this is Ganiki Chasma, which extend into the north, to the northwest, or north. This here is Matman, which is the highest volcano on Venus. It's extended. The height is about 9 kilometers. And this is Azaman, which is the center, the main center of the plume center. This plume that we measured, the large or super plume, is centered at Azaman. We discovered a small center here, which we call unnamed center, and this is also a large center called Vutiman. And those are all high elevation magmatic centers. Going back to Azaman, Azaman is characterized by major, large radiating dikes that extend for more than 2,000 kilometers. And here is the Great Dyke of Atla Regio that extend for about 3,700 kilometers if we calculate the distance just from this small pit here. Well, we think that it might be sourced here. This is the magma chamber that we think is feeding this dike. If we continue to Ozaman center here, this is a large crater of Ozaman. So the dike would be extending for more than 3,700 kilometers. So you see here that the dike is continuing, and this is the small pit or depression of the magma chamber that we are suggesting in this research. And the dike continues until it reaches, and you see how it starts swinging when it approaches this large fluctus or flow on Venus. And this flow here, it extends to about 1,200 kilometers. This is one of the largest flows on Venus. There are a few of them, but this is one of the large flows. As it's approached, it is cross-cutting this flow, so it means that it's cross-cutting, but in some area it doesn't cross. It's covered with this flow. So we interpret this to be coeval with the fluctus, with neo-fluctus. And at exactly a distance of 1,200 kilometers, dike swings, and it continues. It's become linear, so from radiating to linear, and become parallel to what we call Parga-Chasma, this large 10,000 kilometer rift zone. Again, this gives us information that the dike and the Parga-Chasma or rifting are coeval. Maybe I'll let you continue. When it approached this corona, which is called the Ododua corona, and it seems at this interval there's a gap in the dike, and because it is covered by the flows from this corona, which we call Ododua corona. The dike continues. Maybe Richard, you take it over.
And then in this area here, it's very difficult to trace. Right in this area, there's a center there called Momboku Mons to the south there, and so there's a big corona center, volcanic center there, and you see an interruption in the trace of the dike on the northern side there in these really complex radar bright areas. And so we're not quite sure whether it's younger or older there, but we can't trace the dike through that section. It may mean that those structures there, and it's really complicated, and some of those structures may be younger, so we can't trace it there. And then we continue on though, and it's continuous crossing all the other stuff, and then we get to this Onenheste corona, and it has these. You see these linear features; those are Graben, again representing a radiating dike swarm, and those are cutting the dike. And so we know that Onenheste corona is a younger feature than the Great Dyke. By the way, also throughout much of this area, this Great Dyke had been previously mapped as a Penthesilia fossae, a single kind of trough-like feature that had been previously identified to extend 1,700 kilometers. So that's and that's through this area here. And so
it stops. It was not continuous until Ozaman, but it stops somewhere in this area.
We weren't able. It wasn't traced further. Anyway, so we've traced. We doubled the length of what was previously known as a single Graben kind of feature, and to the 3,700 kilometer distance that we talk about now, and we've also confirmed its story as a giant dike. And here we are. There's a little area right there where you see an impact crater, and you also have difficulty tracing the dike, and it's probably because the impact crater produced a lot of dust that has smoothed out everything from a radar perspective, and so we can't see it. Again, that would tell you that these halos, these dark halos associated with impacts, also have a limited age, maybe tens of millions of years before they tend to be disappear from the winds, and based on modeling. So that's another clue that This Great Dyke is younger.
This is Felicia Corona.
Is young. And then we keep going and we reach as far as we can trace the dike.
It's actually cross here because we use another look of image, but taken from another, which is right look. There's two from the Magellan Star images. There was two. There's the first look, and which is the left look. Then another round of imaging, which is called the right look. And when we bring the image of the right look, this is actually covered. We see the geology, and the dike is actually crossing this section.
Okay, we're almost at the end of the dike. We've almost finished our field trip. Here we go. We see it continuous here, and then we get to an area where it's a little bit hard to see. We're not sure how it continues in this area, but there it is. That's as far as we can trace the end of the dike, and then we do not see it further.
We could have traces continuously here, but we're a
little cautious.
Not sure to stop here. But I can see that a little bit it continues here and it's fading, but we want to stop here just because we are sure it's stopped.
There it is. There's our field trip along the Great Dyke of Atla Regio in the Atla Regio region of Venus.
Okay. Thank you for this overview of your work. That's really very insightful and exciting to learn something about our neighboring planet.